This is section 1.2, functions and properties. We're going to start with continuity and discontinuity. Yesterday we talked about continuity, and continuity is simply no breaks in the graph. A graph without breaks. What is new is the discontinuity. And there are 3 types of discontinuity. The first is called removable. And removable is recognized with a hole in the graph. So it would look something like, let me undo this. It would be a graph like this, where there's an open hole in the curve or in the graph. That's removable. The second type of discontinuity is called a jump. And we recognize a jump because we will see a hole and then a jump, a gap. So our curve might go like this. We have an open hole, and then the graph picks up somewhere after it jumps from one space to the next. And our final type is similar to a picture on last night's homework. It's infinite, okay? So infinite is when the graph splits and each one of them heads towards infinity. It's a split heading towards infinity. So if you look at last night's homework, we had a graph that looked like this, where we have 2 curves, the graph is split, and each graph is heading towards some form of infinity. Do you need me to raise the screen up? A little bit? Any questions about continuity or discontinuity? Okay, so now we're going to talk about an easy topic that we already know, increasing, decreasing, constant. Just a quick reminder, increasing, when I'm looking at a graph from left to right, it goes up. So it's going to look something like this. It would be increasing the whole time. This is a graph that's increasing the whole time. Okay? And decreasing, what's decreasing going to be? Left to right, and it goes down. An example again would be like the graph from last night. Both sections are decreasing. I'm just going to sketch one side, so this would be an example of decreasing. But if you look at last night's homework, the last graph, it was decreasing in both sections. Okay? And constant, what's constant? Neither goes up or down, it stays flat. Okay? So that would look something like this. Good. All right, I'm going to pause for a second while you copy. All right, new topic. This is boundedness. Now, it might sound a little scary, but in all honesty, it boils down to think about where you have control of the graph. Okay, you're going to think about where you have control of the graph. So you know a definite value. It's not infinity, it's a set value. Okay, so there are 4 types of bounded. We have bounded below, Anyone want to take a guess on what bounded below would be? I heard below the line, so like below the x-axis. Any other guesses? All right, so let me do an example of a graph that is bounded below. This is an example of bounded below because I can determine the absolute minimum. I can determine the minimum location. Okay? All right? If that's bounded below, what is bounded above? I know where the exact ultimate maximum is. So bounded above would look like this. Let me get a good example. You could do like a McDonald's M, okay? Because I know the highest point. I don't know the lowest because it's heading towards infinity. Okay, I told you there's a total of 4, okay? So there's 2 more. The next one is neither. It has no boundedness, and that means I have no control of its max or its min, okay? I might know a local min or a local max, but I don't know the absolute one. So neither would be something, sorry, like this. Because these are heading off to infinity. So I don't know where the maximum is eventually going to be. I don't know where the minimum is going to be because these are headed this way. Okay? And the last one, which I'm going to draw over here and then erase because I made a reminder for myself about something else. So the last one is both. It's bounded above and below. So above and below would look something like this. Oh, sorry. Bless you. Okay, it would look like something like this, okay? It has definite endpoints. They're not going to infinity. And I know the highest point the graph will ever reach, and I know the lowest point it would ever reach. I'll give you guys a couple seconds to copy that, and then, like I said, I'm going to erase so I have space for Estrella. Okay, so give me a second. Let me erase this image. All right. I kind of started covering Extrema when I was talking about boundedness. We have a max, also known as the maximum. I just write max, sorry. The absolute. The absolute maximum, which would be the highest point the graph ever reaches. We also have a local max, okay? So, in a picture like this one here, this right here would be a local maximum, okay? So, it's not the maximum for the whole graph, but it's a maximum at a certain point on the graph. That's the difference between a local and a local and a regular maximum, okay? A maximum has to be the one for the entire graph, and a local could be just in a certain section. All right, so if I have max and local max, I must have min and local min. Okay, same thing. So in this problem up here, I had a minimum, all right? And in this graph over here, this would be a local minimum right there because it's the lowest point. It's a low point on the graph, but it's not the lowest point. It's a minimum for part of the graph. Does that make sense? Okay. And one other little piece, as you see, there's 5 bullets. There's not another type of extrema. It's just so that you know that local extrema sometimes are known as relative extrema. Okay. And if you want, let me move this for a second. Right here is an image. Okay. This one has all of them because it doesn't go to infinity. It has a definite endpoint. You can see that this is a local max because it's a high point on the graph, but it's not the highest point. The highest point would be my maximum. Okay. Here is a, trying to click so it doesn't hit on it. Okay. This is a local minimum because it's a low point on the, sorry, this is the minimum because it's the lowest point for the entire graph. This is a local minimum because it's a low spot on the graph. It's just not the lowest. Okay, so give me 1 second. Can I go ahead and erase this and put the graph there? Because if I leave the words, it'll be a little blurry. Okay. So, here's an endpoint, here's an endpoint. I have a local maximum because it's a high point on the graph, just not the overall high point. This here would be the overall maximum because it's the highest point on the graph. This is the absolute minimum because it's the lowest point for the entire graph. This is a local minimum because it's a low point on the graph, just not the lowest. Everyone clear on those? Okay? So while you copy that, I'm going to take another little pause and then we're going to flip to the back. All right, so a good question was asked. If it's a local maximum or a local minimum, you have to have the word local or relative in front of it. Otherwise, when you use maximum or minimum, that is referring to the maximum for the whole graph. So that's the ultimate maximum. You don't, or absolute maximum. You don't have to use the word absolute. But when you're talking about local, you have to use the word local or relative. Okay, moving on. Symmetry, and you've seen symmetry forever and a day. All right, symmetry looks the same. Also, your teacher might have referred to it as the mirror. When you look in the mirror, you look the same on both sides. You should have seen symmetry in elementary school. You should have talked about it in geometry. Nothing's changed. Name one type of symmetry that you remember. Yes, sir. Butterfly. A butterfly has symmetry, but what type of symmetry? Bilateral, okay. All right, well, which way is lateral? Up and down, okay. All right, so we have up and down would be my up and down is my, yeah, is my vertical, it is my y-axis. Okay, so y-axis, and it would look something like this, yes? If I fold along the y-axis, my picture looks the same on both sides. So we have y-axis symmetry. This arrow up here is going to be important in a second, okay? All right, so I have y-axis or I have x-axis. And x-axis, I'm going to fold it over the horizontal. Now, what can you tell me about that graph? It is not a function. Excellent. So that's very important. Not a function. And we're talking about functions, so we're not going to talk about x-axis. Because if it had x-axis symmetry, it would not be a function. All right. Last one. This stumps everybody. Oh, all right. What you got? Across the xy. We're going to refer to that as origin. Oh, God. Okay. So I had to double check. I always spell origin wrong, so I had to double check the spelling. That's why sometimes I look down at my paper because I got to make sure I got the spelling right. Okay. Origin. Okay. So it can be folded somehow through the origin. So, in this case, I have, let's say that this is 2, 3. This is -2, -3. They have symmetry. So I go from an xy to a -x, -y. That is also a symmetry about the origin. I'll give you a second to copy that. Okay, so I told you these arrows were going to be important. If it has y-axis symmetry, it is known as an even function. Okay? It is an even function. We will also, today we're specifically talking about how you would notice these on a graph, but I'm going to add how you would do it algebraically because we're going to get into that. So if I take f of -x, which means I plug into the function, let's say x was 2, instead I'm going to plug in -2, okay? If I do that, I should get the same original output. That's what an even function does. Even Steven. You ever heard, you lose 20 bucks and then all of a sudden you find 20 bucks? The world works out even. Something goes bad, something good happens to, the world works out. We good? Do they still use that phrase anymore? No, you guys haven't heard even Steven? Okay. Wait, probability 50-50? No? Equally likely chances? No. You disagree with that? Wow, I'm sorry to hear that the world is 75% bad and 25% good. I hope that turns around for you. Okay, origin is going to be odd. And what that looks like algebraically is when I do the flip, my function also flips. Okay? I'll take a moment. Good. And the next one you guys should all know, but we're going to write it anyway. Sorry. Good? All right. What are the two types of asymptotes? Horizontal and vertical. And we're just going to make some quick sketches of what that would look like. So horizontal asymptotes, run with the horizon. That's an example of a horizontal asymptote. This would be an example of a vertical asymptote. This would be written in the, let's say y equals 1 would be that one. And this one would be x equals -2 if I was really counting. All right. Good? All right. Last piece, and then we're going to practice some of this. Okay. Lead coefficient. What is a lead coefficient? The number in front of, say it again. Thank you for adding that piece, in front of the highest power, okay? Because sometimes they try to trick us and they give us a polynomial that's out of order. You got to put it in order, and it's the coefficient in front of the variable with the highest exponent. Good? Okay, so when I look at the lead coefficient, it will either be an even number or an odd number. Okay? Good? So 2x to the 4th or 3x to the 5th. All right. Oh, we're looking at the power. The power. It says lead coefficient, but we're looking at the power. This is the power. Sorry. Okay. If the lead coefficient is a positive number, then as x heads towards -infinity, y will head towards, who wants to take a guess? Infinity. Because what happens when I take -2 and I square it? It becomes positive. If the exponent's even, it'll be positive. If it's odd, it'll be negative. That's why this works. So, all right, You just answered the next question for me, right? If it were, well, let's finish this one, sorry. As x heads towards infinity, y is also going to head towards infinity. Because if you square a positive number or you square a negative number, it's always going to be positive. Now, the problem happens when you have something like negative x to the fourth plus 5x, let's say, right? What does this negative right here out front really mean? A negative 1, it means negative 1 times x to the fourth power. So, as x is heading towards a negative number, okay? So let's say x is negative 2. Negative 2 to the fourth power is going to be 16. But then I have to multiply it by this negative 1, making it negative. So y would go towards negative infinity. Again, when in doubt, try a number. When in doubt, try a number. It'll make life easier. So this time, I'm going to pick a positive number for x. What number would you like me to choose? 6. 6 to the fourth power. I know 6 to the third is 216, and then I multiply by 6. That's a 6, carry the 3, 9. Hold on, I got to write it out. I lost track already. 6, carry the 3, 9, 1296. Okay. Positive or negative? Positive. But then I have to multiply it by a negative 1, so it's going to be negative. Make sense? Okay? So that's what happens with evens. Now let's look at what happens with a odd. Give me an example of an odd. Not an odd number, but an odd power. X to the third. I heard 3, but I want to hear x to the third. All right, cool. So we have positive, meaning the number out front is positive, and negative, meaning the number out front is negative. So here we have x to the third. Here we have negative x to the third, right? Which really means negative 1 times x to the third power. Good? Okay. So right now, did everyone get this copy? Because I wrote too big, so I need to erase and make some room. Okay. All right. So we're done with even. We're looking at odd. I still have not figured out how to write small enough. All right, so odd would be like x to the third, x to the fifth, x to the seventh. We're going to look at positive. So if the lead coefficient is positive like here, we get as x heads towards a negative number. Okay, so if I put in negative 3 here, what am I going to get out? What type of number am I going to get out? A negative number, so negative infinity. Okay, negative infinity. All right? As x goes to a positive number, give me a positive number, 6. So 6 to the third power, is it going to be positive or negative? So y is going to head towards positive infinity. And right up here, this was a negative infinity. Squeeze. Okay? Now we're going to look at a negative lead coefficient. So if I have negative x to the third, this really means negative 1 times x to the third. So as x heads towards negative infinity, so let's say x was negative 2. Negative 2 to the third power would be negative 8. But then when I multiply it by a negative number, it becomes positive. So y would become positive infinity. As x goes to infinity, a positive number, we'll go with 6 because somebody's obsessed with 6 in here. 6 to the third power is 216, and then when I multiply it by a negative 1, it is negative infinity. And that, ladies and gentlemen, is all of the notes we need.